Resonance is a phenomenon observed in systems that tend to oscillate at some fixed frequency. This frequency is called the natural frequency of the system. If the system oscillates at its natural frequency under the influence of an external periodic force, then the amplitude of the oscillations is noticeably larger than those at other frequencies. Consider 4 pendulums P, Q, R, and S suspended from a rigid support as shown. The lengths of the pendulums P and Q are equal. The lengths of the other 2 pendulums R and S are different from that of P and Q. Initially, all the pendulums are at rest and hence do not oscillate. When the pendulum P is made to oscillate, after a certain period of time, all the other 3 pendulums oscillate as well. Here, the oscillation is due to an external force, which is from the pendulum P. Out of the 3 pendulums Q, R and S, the length of pendulum Q is equal to that of pendulum P. Hence, the natural frequencies of these 2 pendulums are equal, and this gives rise to the situation where the pendulum Q oscillates with increasing amplitude due to resonance. This is an example of resonance in mechanical systems. Similarly, the phenomenon of resonance can also be observed in electrical systems. Let us now study about the phenomenon of resonance in an LCR series circuit. We have seen that at any instant t, the applied AC voltage is represented as V equal to Vm sin omega t, where Vm is the amplitude of the AC voltage and omega is its angular frequency. At the same instant, the current in the circuit is given as I equal to Im sin omega t plus phi, where phi is the phase difference between the AC voltage and the current. The phase difference, phi, can be calculated by the expression tan phi equal to xc minus xl by R, where xc is the capacitive reactance, xl is the inductive reactance, and R is the resistance. We know that the amplitude of current Im in an LCR circuit is given by Vm by Z, where Z is the impedance of the circuit. In terms of capacitive reactance Xc and inductive reactance XL, we have Z is equal to square root of R square plus Xc minus XL square. Substituting the value of Z, we get Im as Vm by square root of R square plus Xc minus XL square. Let this be equation 1. We also know that Xc is equal to 1 by omega c and XL is equal to omega L. For resonance in an LCR series circuit, the amplitude of the current in the circuit should be the maximum. For this, the necessary condition is Xc should be equal to XL. Substituting the values of Xc and XL in the expression, which is the condition for resonance, we get 1 by omega c equal to omega L, or omega square equal to 1 by LC. On further simplification, we get omega is equal to 1 by square root LC. Let this be equation 2. Let us now call this angular frequency as omega naught. This frequency is also referred to as the resonant frequency of the circuit. We observe that as omega is varied, the value of current changes and is maximum when the value of omega is equal to omega naught, such that XC is equal to XL. As the impedance Z of the circuit minimizes and becomes equal to R. This is the condition for resonance. Now, equation 1 can be written as Im is equal to Vm by R. Thus, we observe that when the angular frequency omega of applied AC voltage becomes equal to the resonant frequency omega naught, the amplitude of current Im reaches its maximum. Resonance is possible only in a circuit which has both capacitive and inductive components, as the condition Xc is equal to XL needs to be satisfied. Thus, resonance can be observed in a series LCR circuit or in a series LC circuit, and cannot be observed in RC or RL circuits. This can also be observed from the graph of Im plotted against omega, with Im on the y-axis and omega on the x-axis. Here is a sample graph for the amplitude of current Im versus angular frequency omega, plotted for the values L is equal to 1 millihenry, C is equal to 1 nanofarad of an LCR circuit with two different values of resistance R. The first plot is for the value R equal to 100 ohm, and the second one for R equal to 200 ohm. The amplitude of the source voltage Vm is taken equal to 100 volt. For the given set of values of L and C, we find that the value of omega naught is equal to 10 power 6 radian per second, which is equal to 1 mega radian per second. From the graph, we see that the amplitude of the current in an LCR circuit is the maximum when the angular frequency omega naught is equal to 1 by root LC for either of the resistance values. For other values of the frequency, the amplitude of the current is less than that at the resonant frequency. We also observe that except for the case of resonance, for every single value of Im, there are two values of angular frequency omega 1 and omega 2 respectively, one lesser and one greater than omega naught, which lie symmetrically on either side of omega naught. Let us consider the specific case of the frequency at which the amplitude of the current is 1 by root 2 times the maximum value of the amplitude of current, I max, at natural frequency. Let the corresponding angular frequencies be omega 1 and omega 2. From the graph, we have omega 1 is equal to omega naught minus delta omega, and omega 2 is equal to omega naught plus delta omega, where delta omega is the difference between omega naught and omega 1 or omega 2. Hence, the difference between omega 2 and omega 1 is equal to 2 delta omega. This is known as the bandwidth of the circuit. The ratio of omega naught to 2 delta omega is a measure of the sharpness of the resonance. A larger ratio indicates a sharper resonance. Let us now calculate the value of delta omega using equation 1 for the angular frequency omega 2. Since amplitude of current is 1 by root 2 times the maximum current at resonance, we get I max by root 2 is equal to Vm by R into root 2. On simplifying, we get omega 2L minus 1 by omega 2C is equal to R. Substituting the value of omega 2 is equal to omega naught plus delta omega in this equation and simplifying, we get equation 3 as shown. Using binomial approximation on the expression 1 by 1 plus delta omega by omega naught in equation 3, we get equation 4 as shown. On simplifying this equation, we get delta omega is equal to R by 2L. Using the value of delta omega obtained, the sharpness of the resonance, omega naught by 2 delta omega, can now be written as equal to omega naught L by R. This is also referred to as the quality factor Q of the circuit. Since omega naught L is equal to 1 by omega naught C for resonance, we can also write equation 4 as Q is equal to 1 by omega naught CR. Let this be equation 5. From the expression omega naught by 2 delta omega is equal to omega naught L by R, and the expression Q is equal to omega naught L by R, we get the bandwidth of the circuit as 2 delta omega is equal to omega naught by Q as shown. This indicates that a higher value of the quality factor leads to a sharper resonance as the bandwidth decreases. One of the important applications of LCR series resonance is in the tuning of radio and TV receivers. The circuit diagram shows a typical arrangement consisting of an LCR series circuit used for receiving signals. In this arrangement, the antenna receives various signals and feeds it to the input. This induces a signal at the coil of inductance L in the LCR series circuit. While tuning, the capacitance in the circuit is varied, such that the resonant frequency of the circuit becomes nearly equal to that of frequency of the radio signal being fed at the input for a particular value of the capacitance. Now, the amplitude of current in the circuit becomes the maximum, and we get a high quality factor as delta omega is the minimum at resonance. In this manner, the LCR series circuit can be used to tune into a large number of frequencies of signals in radios and televisions. We observe that when the resonance is less sharp, the selectivity of the circuit will be lesser, as there will be a large range of delta omega frequencies for which the LCR series circuit will be close to resonance. We also observe that for a large quality factor, we should have large value of L or a low value of R for the expression Q is equal to omega naught L by R.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे जरूर लिखिए। थैंक यू।